Alright, so let's go ahead and take a look at this problem number 8, continuing on our little trend wonderful thing. So just finishing problems, doing more stuff. So I'm going to actually draw AX and AY in this problem in red, and I'm going to draw the X and Y components of velocity in blue. So continuing on this trend, first what I want to do is I want to take this little VX here and fill in like a little arrow for it. Hopefully I didn't do this really badly, so there we go. Wonderful. Now, to really emphasize this fact, let me just go ahead and draw this little V here and a little X there like that. And this is really the trend that I want to show you. So Vx in this situation is the following. I'm going to take this. Oops. I'm going to take it, lift it up. This is a little trickier than I thought. Let's try it one more time. Whoops. So I want to cut it, and I want to paste it so that it goes where we want it, which is over here. Let's do it again, just to really emphasize what's going on. Okay. This is really what's happening with this whole Vx thing, is that it absolutely does not change at all as the cannonball goes through the air. So this is just wonderful. That's Vx. Okay. Now for Vy. Vy is interesting because it actually does get smaller and smaller because of gravity. So what happens is here we actually end up getting just a little bit smaller. So this is Vy, and so our resultant V actually gets a little flatter. And then of course our resultant V here is actually equal to Vx, our speed. Okay, and then here Vy actually ends up going a little bit downwards. So we actually end up getting a resultant. So this is Vy. And then here we get Vy like this. So if we were to draw a resultant velocities, they would actually look like this. So I didn't want to interrupt the... and you know what? Just to kind of be careful about this, I'm going to actually see if I can erase this little Vx here and move it up, because I really want you to see what this vector is. So this is Vx, and then Vy goes like this. Or sorry, not Vy, V total goes like this, and Vy is this little vertical part here. And then once again, let me just try to repeat that process for the Vx here. So we're actually going to end up getting Vx going horizontally like this, and the resultant V is going like that. And that's really the idea. Now that's the accelerations. Now let's draw that's the velocities. Now let's draw the accelerations. The accelerations are going to actually be very straightforward. There's one thing that we get. The acceleration is AY, and that's equal to negative 9.8 meters per second squared. So once again, just to emphasize this, I want to be really clear on how this works. So let's just take this guy here, and if I can do it, copy it, paste it, and this is really what our acceleration looks like. Here, 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 hopefully. I know it looks a little messed up when I copy it like that, but this is really the point, is in this setup here, like the arrow really doesn't change length. It doesn't do anything like that. So again, the acceleration is in exactly one direction. It's downward, and it's caused by gravity. There's really very little else to say about this. I just want to erase this and write it a little better. So it's exactly the same length arrow, And once again, this is kind of true for both of them. So it's AY is negative G. And again, here, it's just the same length arrow. And that's AY equals negative G. There's really not a lot to say about it. So, and the other thing, there is no acceleration in the x direction. So we've got 3 different colored vectors here, just to kind of be clear on how we've labeled them. Just so if we're going to label this, okay, this is the resultant velocity. These are Vx and Vy. And this is the acceleration in the y direction. And just remember that ax equals 0. There we go. Now, what we have here are a series of problems that we're just going to go ahead and work out. So I'm going to see if it's actually possible to kind of highlight and paste. It looks like it may not be, so that's okay. So we have a stone thrown horizontally at a speed of 8 meters per second, striking the ground from the edge of a cliff. So let me just see if it's possible just to kind of have this problem up here. That looks nice. And then let me see if I can kind of shrink our little writing surface so that we can always have a view of the problems as we're working. So hopefully this will work out. Let's turn the page here. And let's try to go and do problem number 9. And that'll be actually a good place to stop at the end of this video. So, oh, I see. So it does kind of work that way. So that works out pretty well. So I'll move this here. And yeah, we're good. So with that in mind, let's go ahead and take a look at problem number 9. So problem 9 says a stone is thrown horizontally at a speed of 8 meters per second from the edge of a cliff. And of course, our goal is to figure out how from the base of the cliff the stone will strike. So with that in mind, here's a cliff. Now, we're going to fire this horizontally like this. 8.0 meters per second, and the cliff is 80 meters high. So here, let's label some letters. We've got y naught equal to 80. We've got y equal to 0. What else do we have? We have x naught equal to 0. And we have some kind of x here that we don't know what it is. So the stone's going to kind of fall like that. And since this isn't our traditional projectile motion, where we start like this, we can't use our nice formulas. We got to use kind of the messy ones. So let's get our formulas written down. We have, if we look at our formulas, we're going to have y equals negative 1/2 gt squared plus v naught yt plus y naught. We're going to have vy squared equals v naught y squared minus 2g y minus y naught. We're going to have Vy equals negative GT plus V naught Y. There we go. And then in the x direction, we're going to have x equals negative V naught x times t plus x naught. And that's it. Now, we want to know how far from the base of the cliff the stone will strike the ground. This is interesting. This is actually kind of a trick question. So first, let's get the hang time. And the way I'm going to do that is let me see what numbers I can plug into the formulas. So I know that my V naught Y is going to end up being 0. And I know that my Y naught ends up being 30. And finally, I know that my Y is going to be, in fact, 0 because I land at 0 elevation. So this actually may be something here when so 0, t doesn't matter, but I don't know what it is. This is 30. So let me see, again, this is just like what we did in the previous unit. They asked me for the x distance, and I can't get that right away because I don't have time. So maybe I can solve for time and just see what happens. So we'll try to do that now. So I'm going to go ahead and plug this into the formula for the y. And so when I do that, I'm going to get 0 equals 1/2 times negative g times t squared plus 0 plus 30. So this ends up being 80 meters high. So I get 1/2, which is negative 4.9 t squared plus 80. So I'm going to end up getting negative 80 equals negative 4.9 t squared. And I'm just going to tell you right now, because I happen to know a little bit of math here, this is going to be about 4 seconds. Okay, a little bit under 4. So when we actually work that out, we'll get 80 divided by 4.9. We take the square root. It's a little bit over, so yeah, about 4 seconds. That's perfect. Now we can use that in the x formula. So we have x equals 8.0 times t, which is 4 seconds. And this works out to about 32 meters. If you had the other one, I think it'll be 32.32 meters or something like that. So we're going to continue doing more problems in the next video.